All right, so when we move from an atom, a neutral atom or element, to an ion, how does that change the size of that ion relative to its atom? We call that the ionic radii, as opposed to the atomic radii that we talked about in the previous chapter. So let's think about this conceptually. So if we have this picture on the left, which is sodium atom, so this is the neutral, or oxidation state is 0, sodium, which is here. If we look at its electron configuration, that's a 1s2, 2s2, 2p6, and then 3s1. And the critical part there is that sodium's got this electron that's stuck way out in this much bigger shell, right? It's staying way out here. But if we ionize this and we allow it to revert back to its sort of neon closed shell, what it wants to be, sodium plus 1, then what we've done is effectively eliminated that electron in the largest shell, and we've contracted the whole ion to be much smaller in radius than the original atom. And so sort of the general rule here is that if you remove an electron from a higher shell, that's going to contract. And so the ion is actually going to be smaller than the atom was in that sense, specifically cation, so the positive ions. When we've removed electrons, we get much smaller. And that should make some sense because we get rid of that electron way out there, and we've also increased the effective Z, the nuclear charge, meaning this whole thing starts to contract inward more because we have less shielding effect on those outer electrons. And we can see that trend to be true as we track across the periodic table. So if we go from lithium to sodium, potassium, rubidium, cesium, so that's just moving down this group 1A column, you can see the size or the radius of lithium atom, that's 0 valent lithium versus lithium plus. We get a significant drop, almost by a decrease in half or more, just by popping off that extra electron. And that trend exists as we move down the periodic table, and it also exists in group 2A for the cations in this case. So that's the general trend. So for cations, if you pop an electron off, the shell shrinks to the next smallest principal quantum number, and you get contraction as that dense positive nuclear charge drags those electrons closer to the nucleus. So let's think about then anions, so things like the halogens in the group 7, so chlorine, so this is 0 valent chlorine here. Chlorine has this 3s2, 3p5 subshell fill. If you tack an extra electron onto it, which is what it wants to become the noble gas configuration, it's not actually increasing its principal quantum number like cations. It's actually just staying in this same n=3 shell. But what we see as it gets larger. So we're tacking an electron on and it gets bigger. That maybe makes some intuitive sense. Let's try to hand wave some rationale there too. So because it's getting bigger, I mean, why? It's not actually going to n=4, so we're not getting a bigger shell here, which is what happened with the contraction of cations. It's staying in the same shell, but what is happening is the electrons that get added to this same outer shell have greater shielding, meaning there's more blockage of this positive nuclear center to this every time you add another one, which means that it slowly expands because the Z effective is getting smaller and smaller. Z effective, remember, is essentially this charge. So this electron out here isn't actually feeling a positive 17 charge, it's feeling some fraction of that based on how many electrons are in its path between it. So it's the Z effective that causes the slight swelling of anions when they are created relative to their atomic counterpart.